And now let's once again consider the potential from a point charge, given that we now realize that the change in potential is related to integrating the E field across a given spatial extent. So here we have Q, and we have an electric field produced by Q. And here we have 2 points A and B, so we'll extend a line radially through them, and point B is out at infinity. So here's at position A, we have the radius, basically the radial extent at that location. And then from A to B, we have this path, and we have a little dl here. We'll call that dr. Don't have to worry about it because it's all in line here. So VA minus VB, the potential at A with respect to the potential at B, which is at infinity, is integral from A to B of E dot dl, which is E cosine of theta dl, and cosine of theta is always 1, so that's nice. So VR minus 0. And 0, of course, because VB is 0. The radius is infinite out there. Integral from R to infinity of E dr. Now, the electric field is K Q over R squared. So the integral of 1 over R squared, of course, is negative 1 over R. So we have VR equals negative Q over 4 pi epsilon 0 R from R to infinity. Negative sign is out in front here. And this is 0 when we stick infinity in there, minus a negative, and we have the potential from a point charge being KQ over R. Now finding V from the electric field instead of energy per charge should give us the same result, but can be very useful and typically a lot easier. We just have to integrate the E field through space to figure out the potential difference between those two regions of space from a point charge, or actually from any charge distribution. That general idea will work as well. Woohoo! That's great. Well, let's do an example problem considering point charges. We have a 12 nanocoulomb and a minus 12 nanocoulomb, certain distance apart, fixed in position. We have 2 points A and B, and A is 4 centimeters from the plus and 14 centimeters from the minus. We're going to determine the potential at A and at B. So what we're going to do, well, the nice thing, the thing that'll make this really simple, is that the potentials add algebraically. It's not a vector quantity, it's a scalar quantity. So that's very sweet. At A, let's do it. So the potential at A is the result of potential from the 12 and the minus 12. And potential from a point is KQ over R, so there's K. Let's factor out the K and put the 12 nanocoulombs over 0.04 meters, and then a minus 12 nanocoulombs over 14, or 0.14 meters, giving us 1930 volts. We're done. That's the potential at point A. At B, well, don't really have all the information here, do we? What's this? I didn't give you that. We actually don't need it because, well, this is symmetrically positioned along here. The same distance between the two charges. So we could compute what that potential is from one of them, and the other one would be the opposite sign. And so when you add two numbers of opposite sign, same magnitudes, you get 0. So that's what the result would be at B. But now let's make sure that that's consistent with an analysis of the E field, integrating the E field across space. So here we have B. The electric field from the positive, the 12 nanocoulomb, is pointing like this. And from the other one, since it's toward, gives us this one. Now those are symmetrical, so that produces an electric field basically horizontal from our point of view here. Now E is perpendicular to the bisector of these two charges. Right. That's kind of nice because if you think about moving the charge along, perpendicular to the electric field is not going to do any work on it because the force is perpendicular to the displacement or the motion. So if we move a charge from B out to infinity, go all the way out to infinity, we should expect that the integral from B out to infinity of the E field is going to be 0. The work is 0. But does it really require us to move it along that one specific path? Do we have to go this way? Or I wonder if we can go this way. Well, yes, we can. But can we do anything else? Well, from what we said, the potential at B is 0 because it doesn't take any work to move a charge from B out to infinity. That's a good definition of 0 potential. The potential with respect to infinity is 0. So it takes 0 work to move a charge anywhere along the bisector and 0 work to move a charge from B to infinity along any path. So it turns out that we could take a charge at B and move it around here, boom, and go this way, and whatever we did. When you integrate that entire path, E dot dl, we're going to end up with 0. We can go into more detail analyzing the intuitive reasonability of that. I invite you to do that. Now let's place a 4 nanocoulomb charge at A. There it is, 4 nanocoulombs. What's the potential energy of the 4 nanocoulomb charge? Now in asking that, it's with respect to the 12 and negative 12 nanocoulomb charges that are fixed. Now you might see right away that, well, the 12 is a lot closer than the negative 12, so the push effect is going to be greater than the pull effect from this one. Which means that if you just let this go, it should shoot away from the system. So there's some potential energy there, because when you let it go, it has the ability to do work, and it should be positive, right? Well, let's check this out. The nice thing is that we've defined potential. It's energy per charge. Well, we're looking for the energy, so energy is charge times the potential, Q VA. And we have the Q and the VA. That's
child's play.
Indeed. It's very simple, and that's very nice for us to do problem solving. If you know the potential at a point, then getting the potential energy is likewise very simple. Well, with our current understanding of how the potential changes through an electric field and potential energy of charges is related, we can define an electron volt. So let's have an electron in an electric field moving from A to B. So there it is. And it's an elementary charge, say E minus. So we have potential at A and we have potential at B. Now since V is equal to potential energy per charge, based on that charge Q here, then we can say that UA minus UB equals Q VA minus VB, which is Q VAB. Now for an electron, the change in energy in moving from A to B is UA minus UB, and that's the Q, which is elementary charge E. So there's that, VA minus VB. So that's the change that the electron goes through, and you could say then that it either obtains, gains, or loses kinetic energy equal to that much. Well, if the potential difference that it passes through is 1 volt, then VA minus VB is 1 volt, and the change in energy is E joules, because the potential difference is 1. And E, the elementary charge, is a known quantity. Therefore, we have the definition of 1 electron volt, which is 1.6 times 10 to the negative 19 joules, the unit of energy that's common in particle physics.